Right. Let's do another example. Here's another one. So let's say now we have a group of students, okay? They took an exam. The exam was out of 100. And I presented the scores here. Through this histogram. Okay. Now, the question is, how many students took the exam? Well, it's really just like what we saw before. How do we get the number of people they questioned? Or in this case, how do we get the number of students who took the exam? Well, you add up the frequencies. We add up the frequencies. I mean, you can almost think of it as who's ever running this experiment asked, each individual student what their exam score was. And I guess we're assuming each student was honest enough to give their score. Or somehow they got the score otherwise, I guess. But anyway, so we add up the frequencies, right? So this is saying 2 students had an exam score greater than or equal to 0, but strictly less than 5. So no one actually got a 5 on an exam, right? You don't include the right endpoint. Well, how many students took the exam? Well, we add up the frequencies. We have 2 plus 2 plus 1 plus 2, 1 plus 2 plus 2, 1 and 2 plus 1, 1, 1, 1, 1. And assuming my arithmetic is correct, which I think it is, we get 20. You get 20 students. Wait, on it. There we go. So the second question I asked was, what percentage of the students got a 70 or above? Well, we're going to look at this data. As you can see, 70 or above is here. Okay, that's cool. Well, how many is that? We add up the frequencies. We have 1, 2, 3, 4, and 5. So it's 5 out of 20 times 100, right? We're asking now what percentage is 5 of 20? Well, 5 is what percentage of 20? So 5 divided by 20 times 100, which is 25%. So that's what we get here. So, just some examples with reading histograms, Are there any questions about this? Well, let's go on to chapter 11 then. Okay, let me get my notes for 11. I did send those out as well. They are, there we go. Okay, so this is 11, chapter 11. Here we're going to look at describing data. We're going to look at a few different things here. One, we're going to look at distributions. We'll see what that actually is, a distribution. I mean, I'll tell you in a second, I guess, but I'll tell you now as well. Basically, what you're looking at is all the possible values a variable can have, can give out, that is, and the corresponding frequency. And in fact, we're going to be working with histograms and frequency tables a lot. Most of the stuff here, we're going to work with quantitative data, but we will mention a bit about qualitative data as well. We're also going to look at what we call measures of central tendency. This is actually what you might have expected when you found out we were going to cover stats in this class a bit. This is where we do things like mean, the median, the mode. We're also going to look at standard deviation, variance, and the range. That's how you measure variation of data. how much the data varies from actually the mean. We'll see that as well. And we'll see quartiles also and what they call the five-number summary. There's also something called box plots that we'll make. I don't know if I said this last time, but you can actually make histograms and box plots through Desmos. Although I thought Google Sheets made them look a little nicer, so that's why I stuck with Google Sheets. If you want to see how to do it in Desmos, you can always ask. It's not hard to do. Different. All right. So what is a distribution? Well, it's basically the distribution of a variable. You're specifying all the output from the variable, all possible values, in other words, the variable can take on, all possible values it can give back, in other words, and the frequency of each possible one. So you're looking at the output, so to say, and the frequency. And so that's why we like to look at frequency tables. We will look at histograms as well. You can actually use histograms to present the distribution. I know the book does this. The book actually draws a smooth curve. You can draw a curve to a graphical display like a histogram to also display the distribution. You can do that. I couldn't figure out how to do that in Google Sheets. So, mostly I'm going to focus on histograms because, as we saw, they're not terribly hard to make. You could actually use a formula as well. I know the book also does this. They do go into drawing a curve. I don't know if they go into it, actually. I shouldn't say that. But they do actually have pictures where a curve on a histogram is drawn. And again, that's used to display the distribution. Right. That's what a distribution is by definition. And what we like to do is we like to characterize them by what characteristics they have, what properties they have. One of them, and one of them is basically their shape. There are many different shapes a distribution can take. And with these two, you can use a curve to display the distribution. And what we have here is a symmetric one. A symmetric distribution, that's one where if you imagine folding the center of it so that the left and right hand side, folding about the center, and the left and right hand sides match up. Or maybe a better way of saying that is where the left and the right hand sides are roughly mirror images of each other. Or again, if you imagine whatever the center is and you fold along the center, both halves would match up. So this is actually one that's symmetric. Here's another one here that's actually symmetric. I'm not sure what the center of this thing would be. Here it looks like the center would be the y-axis. If we fold it along the y-axis, these two curves would match up. Another one is what we call a skewed distribution. This one is actually not symmetrical, as you could probably see from here. But in this case, what happens is the data clusters towards one side. Because of that, you'll actually get sort of a peak, which is, like the peak of a mountain at the highest point. Not sure if that's how it's formally defined, but intuitively that's what it is. The other side, you'll have sort of like a tail. So it's not symmetrical like this, where it's more evenly spread out, I guess. Here, the data is clustering towards one side. And on the other side, you have sort of a tail. You say this is left skewed because the tail is on the left side. Here it's right skewed because the tail is on the right side, as you can see. So this is not symmetrical. You can imagine that whatever the center is, if you were to fold it along the center, the left side and the right side would not match up. So this is not symmetric. Asymmetrical, in other words. Here's actually an example of one that is symmetric. I know it doesn't look exactly symmetric, I understand that, but you can imagine taking a center which looks like it would be around here, and you can see how, well, the left-hand side and the right-hand side, they're not mirror images of each other, but they're pretty close. And if you imagine folding this thing along the center, along a vertical line in the middle, both halves would not quite overlap, but they would roughly overlap. As I have down here, they may not fit exactly the descriptions of the shapes as described. That can happen. In other words, both halves may not line up exactly. They may not overlap exactly if you fold along the middle. But if it's close, then we'll say, it's symmetric. All right, so that's what we have here. Okay, are there any questions so far? Okay, if you're confused about anything, don't be afraid to ask. And if I go too fast, don't be afraid to say something. I know I want to get through chapter 12 before the semester ends. But if I don't, that's okay. I'd rather, everyone understand what I'm trying to teach. So that's basically the idea of that's what it means to be a symmetric, a left skewed, and a right skewed distribution. We have this definition of an outlier. The book is not going to go into this too much. So I don't want to go really far beyond the book. So I'm not going to go into it too much either.